Okay. I will try to go slightly fast. This talk is not super long, but thanks everyone for coming. Nice seeing you here. So this talk will be more of a see how things work together rather than this is a super new thing, because if you've been following some of the packages that have been developed in the JuMP ecosystem, you could see many of these coming. And yeah, I think it's a just great case on how you can integrate things and most of it works really easily. So the idea would be differentiating parametric JuMP models. So let's go for details. What do I mean by differentiable optimization and differentiating these parametric problems? So what I mean is we have a set of parameters, so from theta 0 to theta m. Each one of them can be a vector of parameters, that's even fine. Then you define an optimization problem, P, in which you have an objective function that can be parametric and a bunch of constraints that can be conic and depend on parameters as well. And then you can solve this optimization problem. You get your X star, and then here comes the thing that it's usually different from most of the things that we are used, which is, well, now we want to differentiate the solution of this optimization problem, X star, with respect to the parameters, okay? So, well, Andrew made kind of a use case introduction for some of these, and I will talk slightly more about some applications and then go into more details on how we can achieve this. And, well, the alternative way of saying that is we want to differentiate the solution of a parametrized optimization problem. So I made these two words on bold, and we'll see why soon. So besides Andrew applications, I like to mention that we can use this differentiable optimization for a few different use cases. One of them is in classic operations research, to compute sensitivities, perturbation analysis, or even solve bi-level optimization problems. But also, like Andrew was saying, there's a bunch of new ML stuff, and you can put your optimization problem as a layer in between neural networks. You can do hyperparameter tuning, you can do some learning. I was especially interested in actually these two things. One of them led to the development of bi-level JuMP, and the other one of my papers from my PhD, in which I was doing these learning type of algorithms in which, like Andrew said, you want to optimize your forecast given the final cost of your application. But then, remember the sentence, differentiate the solution of a parametrized optimization problem. And this might be a lot of work if you were back in the day, but we can get some help for doing that. And one of the sources of help is Google Summer of Code. We had some very nice students working on projects related to this a few years ago. The first one was Akshay, that was working on optimization problem differentiation, which led to the development of the DiffOpt package and the follow-up paper that we developed. And it's very interesting because, well, again, seeing some of these JuMP macros, I think we're going to see a bunch of them during this meeting. In this case, let me see if I had, oh yeah, this is perfect. So you define your optimization problem as usual. The only difference is that you put a DiffOpt optimizer layer on top of your solver, in this case highs. And then you can try to query the sensitivities. In order to do that, you have to tell which sensitivities you'll be querying. And to do that, you can define scalar find function, which says basically I'm differentiating with respect to the constant of this function. And then you can pass the sensitivity function to your model. Then you compute forward differentiation, and finally you query the forward derivative of the variable x. Well, defining this function this way and getting the sensitivity this way is basically what you need to do if you want to be super general, because you might want to differentiate with respect to any coefficient of your problem. And that's all you have. You have the coefficients of your problem, and you want to figure out how to differentiate with respect with each one of them. But this might be a little cumbersome for some reasons, like defining this function sometimes is a lot of work. Sometimes your parameter will appear in a bunch of coefficients. Sometimes your parameter is multiplied by some constant and things like that. And also, you have to be careful because you can see here that the derivative of x with respect to a change in the right-hand side is -1. And the reason is, well, this function that we are computing the sensitivity is actually a constant on the left-hand side because JuMP normalizes things. So this is also a little bit of care that users sometimes get confused with. Sometimes people start using DiffOpt and they say, why this minus sign? It should be the right-hand side. And like, nope, actually, it's the left-hand side constant over there. The second project that we had in the same year, in 2020, was adding parameters to JuMP and MOI. So it was the first sketch on how to do that. Well, not the first. We had parameter JuMP before that, but then we were like, how can we do that considering MOI? And then it was a great project. It led to ParametricOptInterface, like Mayo said. And afterwards, like Mayo said, Oscar and the group added parameter to JuMP. So you can now use parameter in the JuMP interface. It doesn't do anything very special, but if you use extensions like ParametricOptInterface, you can get most of it. Actually, it's especially interesting for nonlinear nowadays. So if you're using the new nonlinear syntax, the parameter is the way to go for parameters in nonlinear. In here, again, a little bit of more JuMP code. Now, again, you're doing everything as the same, but now you're wrapping the highs optimizer with the ParametricOptInterface or POI Optimizer. You add your problem. One of your variables is special because it's actually a parameter. And then you can add constraint objective. You can optimize, query the value, but you can also change the value of the parameter later, and then re-optimize and re-query the variable, which is usually super useful for many applications like stochastic programming or what Andrew was mentioning, because you don't need to rebuild your problem, and if your parameter is multiplied by some constant like 3, you don't have to remember that. You can just modify the parameter and everything will be fine. And now, what is the core of this talk is this final slide over here, almost final, which is the differentiation of a parametric JuMP model. It's almost the same as the previous one, but now we're nesting things together. So now we have a bunch of optimizers in place. We start with the highest optimizer, which is contained in a DiffOpt optimizer, and by its turn is inside of a parametric optimizer. And the cool thing here is that all these layers, they work together, and you can add your variables like you would do. You can add your parameters. You can add your constraints, objective. You can optimize your problem. The solution will be the same. But now you can compute the derivatives in a much more straightforward way because you're differentiating a parametric optimization problem. So you set the sensitivity that you want to query with respect to that parameter. So now, instead of saying, I meant that constraint and the constant term of that constraint, now you can say directly, differentiate with respect to this parameter. You compute forward mode differentiation, and then you can query back your derivative with respect to x, which is now is 3 because 3 is multiplying the p over here. And of course, because we have parameters, you can reset your parameter to a new value. You can re-optimize, and you can query again the derivatives, which won't change in this case because it's a constant. Great. So this is actually almost ready. There is a PR on ParametricOptInterface about it, but if you're interested, you can use the PR. I think Andrew is already using that for some of the things he did. So, yep, the PR that is already there. There is something in the PR that we need to fix because currently DiffOpt needs to be a dependency of POI, and DiffOpt is super heavy, while POI is not heavy at all. It only has one dependency. But we can do something, like Miles was saying, we can use a weak dep plus extension approach, and that we need some adjustments, and that should be fine to merge right after that. And the next thing, which is cool, is, well, this new interface, it's simpler to set sensitivities because it's more direct. Instead of figuring out where the coefficients are, you just say where the parameters are and differentiate them. It's simpler to query the derivatives because if the parameter shows in a bunch of places, it will grab everything together and accumulate the derivatives. You can easily resolve your problem, which is one of the cases in bi-level optimization, because you will be resolving the problem as a step in your wherever nonlinear optimization algorithm. And finally, this is easier to generalize, for instance, to nonlinear, now that we have the new nonlinear interface. So that's a follow-up project that Andrew is already playing with in this other PR that is behind the plant. And that's it. So this is differentiating parameters, parametric JuMP models.